Here's a problem on the number 19 out of 25 level on an AMC8. It's modeled after an AMC8, except that the number is chosen in a way that we'll have an interesting discussion at the end also. Suppose you have an isosceles triangle, ABC. Isosceles means that two of the sides have the same length. Angle A is 72 degrees. What are all possible values for the measure of angle B? This is an interesting question because it asks about all possible values. On those, you have to be very careful not to miss one. Well, let's see. All we know is that we have an isosceles triangle. So if we're drawing an isosceles triangle, it might look like this, where the 72 is on top. Or, if you have an isosceles triangle, the only other possibility is that you have the 72 on the bottom. These are really the only two possibilities that you can have. Now, if that's the case, what does this look like? If this is a 72, because the sum of the angles of a triangle is 180, it's actually quite routine to finish this side. 180 minus 72 is 108. These are all very common numbers that you'll see when you do geometry because of the way that the additions and subtractions and multiplications of small numbers are. And this 108 is going to be split into two parts, 54 and 54. On the other side, if I have two that are already 72, 72 plus 72 is a nice number. It's 144. And what is left when I subtract from 180 is just 36, which is also nice. So if I have this, this tells me that these are the only possibilities. And the question is asking me for what is the measure of angle B. Now, angle B is the other angle. If I have the other angle, the interesting thing here is that at first you might just say, well, the other angle could be 54 or 36. And those are the things that the other angle could be. This is actually a bit of a trick question. The other angle can also be 72, because it is not that the other angle has to have a different measure. It's just that it has to be a different vertex. So if this was A, this could be B. But so the answer to this question is 54 or 36 or 72. But I wanted to go a bit further. I wanted to talk a little bit about how important and beautiful these two triangles are. The first thing is, how can you even get them in the first place? Where might they appear? The secret is that this 72 has a very good connection to 360, which is the number of degrees in an entire round in a circle. You see, if I take 72 times 5, 5 times 2 is 10, and now I have my whole 360. So actually, both of these triangles appear in interesting ways, like this. If I draw you a perfect regular pentagon, in this perfect regular pentagon, because of the fact that from the center, this should cut out 1/5 of all of the area, 1/5 of the entire round, this is 72. So this is the 72, 54, 54 triangle. At the same time, there's another triangle, which is also the 72 one here, which is 72, 72, 36. There's a theorem in geometry, which I'm not going to go deep into here, although I will say if you like this sort of thing, there is a geometry class that we also run where it's talked in detail, which says that if I think of this as actually living inside a circle, then this is the center of the circle. And whenever I have a center of the circle, if I take a point which is on the edge of the circle, the angle that it makes is 36. So actually, that 36, 72, 72 triangle is this one. This one here is this tall one. So these are the two triangles that have 72 in them. One is here and one is there. I promised you one more thing too, based on the title. The title to this was called Golden Triangle. And actually, this is talked about in very big detail in one of the geometry classes that we teach here. But to make a very long story short, and to just give a hint of something that's true and beautiful, if you take this particular triangle here, this green one, then actually, if you take the ratio of this side divided by this side, that ratio, which I'll write again here, if I have this thing divided by this thing, this is about 1.618, which is what's called the golden ratio, which is actually the ratio between the length and the width of what is considered the most beautiful rectangle. There's actually a lot in here, which is why I wanted to introduce this triangle 72, 36, 72, 72, and to see all of this in the pentagon. But in the end, this is a question where if you want to make sure you get such questions right, always make sure that if you see the word all, try to make sure you have all. That usually requires thinking possibly outside of the box. And of course, it's fun to always do these with actual numbers, which let you talk about something interesting, like the most beautiful triangle in the world.